Okay. The very last section for Chapter 2 involves models, particularly those in which the value of one variable impacts the value of another variable. Very generic statement there, but because of its generic nature, there are a lot of situations in which we can apply these models. Overall, I'm talking about a notion known as variation, and as I mentioned a second ago, it's a way of describing how a change in one quantity produces a change in another. There are a variety of variations that exist. Those that I think are the most important for us are direct variation and inverse variation. And we'll start the discussion with direct variation. And to model this mathematically, let's assume that the quantities are represented by the variables x and y. So in this definition, it says let x and y be any two quantities. We would say that y varies directly with x, or stated differently, directly proportional to x, if the situation can be modeled with the following formula: y equals k times x. Now this k right here is referred to as a constant of proportionality, and it's kind of like the number that links x and y together. It's a way of generating the y value once we know the x value, and in a lot of problems we have to figure out what the k value is in order to come up with the official model for the setting that we're in. Now I want to point out that this is very similar to slope-intercept form, y equals mx, where m is replaced by k and the y-intercept would be replaced by 0. So direct variation is kind of a special case of lines, which is why it's showing up in this chapter. Now, it basically works this way. With direct variation, if two quantities are related to each other through variation, when one goes up, so does the other, or if one goes down, so does the other. So basically, whatever one quantity is doing, that's what the other quantity is doing as well. So if one increases, so does the other. If one decreases, so does the other. So I have some real life examples here. The very last one is a sad fact about Mr. C's life. Anyway, more sales leading to more revenue. Okay, revenue is the money that's brought in, by doing a sale. And of course, the more sales you have, the more revenue or more money that's brought in. So essentially, an increase in sales leads to an increase in revenue. The bigger the mortgage, the bigger the monthly payment, okay, generally speaking. All right, so let's say that you qualify for a 30-year mortgage. The bigger amount of mortgage that you qualify for typically leads to a bigger monthly payment. This is more of a mathy one, geometry one. The smaller the radius of a circle, so if that decreases, then the overall area of the circle would decrease as well, since they're related to each other in a variation type way. Less electricity used in a month leads to a lesser monthly bill. Okay, so if you use a smaller amount of electricity, say in February than you did in January, then you can typically expect your bill to go down accordingly. And the less time I spend at Target, the less money I have to dish out. That's a true statement right there. All right, so in the case of Mr. C shopping at Target, if the time that I'm there is smaller on trip 2 than trip 1, then generally speaking, I'm not spending as much money. Inverse variation is kind of like a seesaw effect, and I'll explain why in just a moment. So again, let x and y represent the two quantities that are related. We say that y varies inversely with x, or that it's inversely proportional to x if we can model the situation with the following. Y equals, we'll have k again, but instead of multiplying k by x, we'll divide it by x. Okay, so this k is still known as the constant of proportionality. And once we find out its particular value based on what's given to us in the problem, we can write the official model for inverse variation. And this is, like I said, it's kind of like a seesaw effect in the sense that when one quantity goes up, the other quantity goes down. Okay, so on a seesaw, one person would go up, the other person actually goes down, and vice versa. It's a two-way street though. If one quantity goes down and it's inversely related to a second quantity, then that second quantity is going to go up. Okay, so here are some real-life examples of inverse variation. When the speed of a car increases, the time it takes to get to the destination decreases. Right? Haven't we all been there before? Running a little late for work or a little late for school. Maybe we're tempted to go a little bit faster, down 8 Mile or 275 or something like that. But the whole reason for going a little faster in your car is so that you can, make up some lost time there. So if speed increases, time generally decreases. The longer a person is waiting to be seen by the doctor, the lower his or her patience. Maybe that's more of a, silly type example there. But I could definitely remember that happening, a lot of times in my life there. All right, so the longer a person is waiting, the lower the patience can be. More of a sciencey one here. The further away two magnets are from each other, the lower the magnetic force of attraction. Okay, so if you increase the distance, the lower the magnetic force of attraction. The higher the price of an item, generally speaking, that lowers the demand of it. Okay, not always, but there are lots of examples where we would see that taking place. For me, it was with Levi jeans. They used to be, pretty affordable, for our budget. But then they kind of hiked up the prices over time, and now I just look for something that's a little cheaper. And this is definitely true here. The more jokes Mr. C tells, the less laughs he gets. All right, and I'm going to put you guys to the test. At the end of the semester, I'm going to tell you, or I'm going to try to remember some of the jokes that I told you at the very beginning of the semester, and we'll see how funny they are at the very end of the semester. All right. I'll have to get out my Crickets soundboard again. All right, so an increase of jokes decreases the laughs. And you know what? I'll own it. Okay, so hopefully you have an idea of what the variations or how they work. We'll go ahead and get to some examples. The first couple of them just get us in the rhythm of writing out formulas for the variation, and then we'll move on to some examples that are a little more realistic. So here it says, write a general formula to describe the variation. It says y varies directly with x. And then afterwards, it says y equals 16 when x equals 2. The key word here is varies directly. All right, and I'm going to do all of these problems in like a conveyor belt fashion, kind of like what we were doing with one of our examples in the lines section. Um, and it's a process that gets pretty, it's pretty easy to get used to, and it doesn't take much time to get used to it. The first step is to decide on what model to use based on the ones that were presented above. Since it says varies directly, we want to consider using this model for the variation, y equals k times x. That takes us to the second step, where we want to find k. And the reason for doing that is so that we can get a more specific model, namely one that would help us to get a y value of 16 when x is equal to 2. And actually using these two pieces of information can help us find k. I'm going to list those out, y equals 16 when x is equal to 2. And basically what we do is we substitute them into our model. So we're going to replace y with 16. We'll leave k as is, but we're going to replace x with 2. And this can be rewritten as 16 is equal to 2k. If we want k by itself, we'll go ahead and divide each side by 2. And we get a k value of 8. That takes us to step 3, which is going to be the last step in these types of problems. And it's basically what I like to call a rewrite step, where we're going to take our model, y equals k times x. Now that we know our value of k is equal to 8, we can write a specific version of this model. Y equals 8 times x. Now, does this work? Okay, would we get 16 if x was equal to 2? For sure. In fact, you can give me any x value now, and I can tell you what the y value is just by plugging it in. So this is what it means when they want us to write a general formula to describe the variation. Not just any old random k value will work. All right, we need the k value that would help us generate a y value of 16 when x is 2. And so that's the whole reason for step number 2. Okay. So once we figure out our value of k, we come up with a model, essentially an equation with that specific value of k. And you can always check that your model works by plugging the x and y values provided back in. And in some cases, they might want you to predict a different y value using a different x value, in which case you would simply plug it into the answer we have in part 3. So what I'd like to do is give you folks a few minutes to maybe take care of this next example, the one on the top of page 2. It says, same instructions. This time, y varies inversely with x. And it tells us that y is equal to 16 when x is 2. All right, so see if you can apply that 3-step process that we just went through, and I'll check in with you in just a couple minutes. right, does anybody want to type in their answer? All right, that's what I got too. So I'll run through my solution and let me know if you guys have any questions along the way. So the model we want to use is y equals k divided by x. Okay, based on the phrase or the word inversely. So that's our model, y equals k divided by x. Move on to the second step where we want to find k. And this information right here, much like in the last problem, can help us do that. Y is equal to 16 when x is equal to 2. Plugging 16 in for y and 2 in for x. We'll see the algebra involved this time would be to multiply each side by 2. That cancels out our denominator on the right. And 2 times 16 is 32. Takes us to step 3. We're going to take our generic version of the model from step 1, blend it in with our value of k, and we get y equals 32, all divided by x. Now you can get a sense of why inverse variation is kind of like a seesaw effect. If we increase the x values, that makes our denominator of the fraction bigger and bigger. And anytime you're increasing the denominator of a fraction while leaving the numerator the same, the overall value of the fraction decreases. Think about Little Caesars again. All right, they usually come with, the hot and ready usually comes in 8 slices. All right, but if you got kids and their friends are over, and you got one hot and ready, a parent hack is to divide that pizza up even further, and there's a consequence to dividing that pizza up, further and further. Each slice gets thinner and thinner. Okay, so if you think of like a pizza, the more cuts that you do in a pizza, the more slices that you try to make, it's possible, but the net effect of that is that each slice is going to get smaller and smaller. Now we won't be working with pizza examples, unfortunately, in the rest of the notes, but we do have some examples coming up that are more of those quote-unquote real-life type examples. Let's start with this one. At the corner Speedway gas station, which they have great coffee, by the way, the revenue R varies directly with the number G of gallons of gasoline sold. Second sentence here, the revenue is $47.40 when the number of gallons sold is 12. Find a linear equation that relates the revenue R to the number G. And if that weren't enough, we want to proceed to find the revenue when the number of gallons of gasoline sold is 10.5. Let's start with our conveyor belt process. Number 1, we want to select the model. If you look at that first sentence, we see the word directly. So right there is an indication of, the choice that we should make for our model should be y equals k times x. They don't want us to use y and x though. They actually want us to use r and g. And let me give you a secret on how you can figure out, what's going to replace y and what's going to replace x. The letter that's to the left of our keyword directly, namely capital R, that's what we replace y with. And then the number to the right of the word directly, the letter G, that's what we're going to replace x with. So y gets replaced with R, k stays as k, but x gets replaced by G. Okay, everybody good with that? All right, there's my hack for you. Remember, our second step was to find K in those last couple problems. And we can get that information from our second sentence. It says if the revenue is $47.40, that $47.40 is a specific value of R. Number of gallons sold is 12. This 12 right here is a specific value of G. So can I have you plug these two values into our modified model and come up with the value of K? All right, so that's how you want to plug them in. Divide each side by 12. And what do we get for K? 3.95. You got it. All right, let's move on to step 3, the rewrite step. So we'll use this modified version of our model along with our newly found value of K. We'll have R equals 3.95 G. So this part of the instructions where it says find a linear equation that relates R to G is satisfied after doing step 3. Any indication as to, or any idea as to what this 3.95 represents in this particular type of problem? It relates to gallons, but G actually represents our gallon quantity. The 3.95 is actually a rate. You can think of it as a slope M, and it would represent the cost per gallon of gasoline. So it'd be a gas price. Yeah, that's like a GPA gas price right there. You know, I'm more for like the academic probation gas prices, you know. But anyhow, we're actually not quite finished though. We need one more thing here. It says, then find the revenue when the number of gallons of gasoline sold is 10.5. So in this setting, there's a fourth step, and I like to call this the use step. We have to use our model from step 3 to figure out what the revenue is when the number of gallons sold is 10.5. And basically, all that requires is us taking our answer to part 3 and plugging 10.5 in for G. So 3.95 times 10.5. And here you can round to the nearest penny. And when you do so, you should get $41.48. Can I get confirmation on that when you guys have it? Rock on. So you can see the importance of needing to find k as soon as possible. If we did not know what our value of k was, then we would not be able to provide an answer to part 4. It'd simply be k times 10.5, and we really couldn't, provide an adequate response. Which is why we go through the process of finding the general equation or linear equation, however they phrase it, on step 3. And once we have that, like I said with the very first problem, give me any other input and I can tell you what the output's going to be. All right, so in this case, give me any other quantity of gas, and just plug it in and tell you how much revenue that gas station is going to bring in. We'll do one more together, and then I have an extra practice problem for you guys to try. Here we have the demand D for candy at a movie theater, which varies inversely to the price P, and that would be price per bag of candy. And the price of candy is $2.75 per bag, which I'd love to see that. The theater sells 156 bags of candy. We want to express the demand for candy in terms of its price. All right, and then we'll use that to figure out the number of bags of candy sold when the price is raised to $3. Let's start with the model part of the solution. It does say varies inversely, so you do want to choose this model instead of the one we used in the last problem, k divided by x. But again, they don't use the variables y and x, they use d and p. So my first question for you is, which variable should we replace y with? You got it. Yep. So there's our keyword. The variable to the left of it is d. That's what we replace y with. Which means that we should replace x with p. So we'll work with this version of our inverse variation, and we'll proceed to find k. And how will we do that? Well, that's where the information in our second sentence helps. It says when the price of candy is $2.75. That's a particular value of p. The theater sells 156 bags of candy. So when the price is $2.75, the general public want and purchase 156 bags of candy. This can be considered a particular value of demand. So let's allow D to be 156, and that's how much is sold when the price is $2.75 per bag. And we'll plug it into our model from part 1. 156 equals k over 2.75. And if you want to go ahead and solve for k and type in the chat bar what you get for it, that would be much appreciated. $4.29. All right. Well, we'll rewrite our demand equation with our particular value of k. D equals 429 all over p. So in the third sentence here where it says express the demand for candy in terms of its price, we actually satisfy that condition after we're done with step 3. Okay, so this is an equation that relates the two variables together, all the while keeping in mind inverse variation. There is that fourth step though, like we saw in the last problem. It says determine the number of bags of candy. That's referring to a new demand, specifically a demand when the price is raised to $3 per bag. So what do you guys expect to happen? Do you expect more bags of candy to be sold, the same, or less bags of candy to be sold? Yeah, it should be less, right? Because inverse variation, if we raise one quantity, the other goes down. So our fourth and final step for this, we're going to use our model from step 3. We don't know what the demand is just yet, but they do want us to assume a new price of $3. And so we'll plug this into our formula, 429 over 3. And let me just punch this in real quick. That comes out to be 143, and that value would represent bags of candy. So it goes down, it drops by 13 bags of candy. All right. But the fact that it goes down confirms that we have inverse variation. Which, this is a little less of a, one of those real life type examples. Well, obviously because of, the current coronavirus stuff. But even before that, all right, I can't ever recall a bag of candy only costing $2.75. And I think part of the reason for that is because I always snuck candy in. Anybody else do that here? I won't tell on you. Just take a quick trip to Target or the dollar store, wear a big old jacket, lots of pockets inside of it, boom, stuff that thing to the max. You come walking into the theater looking like the Stay Puft Marshmallow Man. No, I don't have anything, I swear, as a huge Kit Kat falls out of your pocket. At any rate, though, that's our solution to this example, and I've got one for you folks to try. It is a your turn example. Different setting here. Monthly payment P on a mortgage varies directly with the amount borrowed B. Now, don't get caught up on this 15-year business in the second sentence. That's just the type of mortgage that's being applied for. The monthly payment is $8.99 for every $1,000 borrowed. Okay, so $8.99 and $1,000 are going to be values for either P or B. And like we've seen, that the information in our second sentence can help us find K. And then you'll want to figure out, what is the monthly payment when the amount borrowed is $175,000. So I'm going to give you some time to work on this. I'll check in with you in about 5 minutes or so to see how we're doing. And we'll wrap class up afterwards. All right, folks, I'm going to start jotting down some of my steps here. So direct variation based on the keyword in the first sentence. Varies directly. Replace our variable y with p. Replace our variable x with capital B. Step 2, find k. Which k is my favorite, or not my favorite, my mother-in-law's favorite letter through text messaging. Like, all right, I'm coming to pick up the kids. Okay. We're celebrating Max's birthday at 5. Okay. Anyway, the 899 is a value of P, and 1,000 is a value of B. So that gives us the equation 8.99 equals K times 1,000. And upon dividing each side by 1,000, we get a wacky value of K here. I guess not wacky, just not your typical 0.00899, which I would leave it as is, you know, just to keep a level of accuracy as best as possible for the rest of it. This is sometimes a pitfall for students. So this value of K, does anybody need help arriving at this value of K? Y'all good? Goody in the hoodie? Okay. Well, let me know if not, and I'll be happy to go back to it. Rewrite P equals 0.00899B. Satisfies this part. Find a linear equation. And then there's a use part to this. Find the monthly payment, and the amount borrowed is $175,000. Anybody want to offer their answer? Yep. I'm going to go with Isabel's version. I'm just going to round it to the nearest penny, but yeah, I can definitely see, where your rounded answer comes from. No biggie. So yep, plug 175,000 into the formula. And there we go.